Yeah, so a couple of thank yous to Sandy and Han from the Branch Council for providing the refreshments. I believe they pushed them in a shopping trolley all the way from Carlton down to here, so thanks to them. To Yuval and Phil, the organisers of Data Science Melbourne, to them thank you and acknowledgements that this is the first joint meeting and hopefully many more to come. Also to Ross on camera, thanks for coming along and doing the visuals, and the intention is to put the presentation up on YouTube. And finally, a big thank you to my colleague and fellow Branch Council member, Daniel Vukcevic. Without him, this wouldn't have been possible. He's been instrumental in bringing these two organisations together. And if statistics and data science ever get married, they've already found their best man. So I've done many things. So on to introducing the speaker tonight. Alec Stephenson is a scientist at the CSIRO. He's previously held academic appointments at the National University of Singapore and at Swinburne. He's a very successful data miner, and what I think he's going to do tonight is tell us how to use a statistical surfboard to ride the big data wave. So thank you, Alec.
Well, am I on? Firstly, thank you to the Stat Society for inviting me here. I last gave a talk for the Stat Society in September 2008. Was anybody at my September 2008 talk? Oh, one person, excellent. 2 people. So I gave a talk then on a model for athletics records. So my remit today is to speak in more general terms about data science. So because this is a joint talk, it's slightly different to a usual Stat Society talk. It won't be theoretical in any way. I'm primarily a statistician, although I've kind of moved towards more data sciencey areas, and therefore I'm generally going to speak about my statistical viewpoints on data science. So I'll start by just talking about statistics versus data science and how they fit in, and then discuss a related topic, which is statisticians versus data scientists. I'm probably known for writing R software, which is software used by statisticians. I've also been fairly successful in data mining competitions, so I'll talk a bit about data mining competitions and teach you how to win them. And it's very easy. So in the middle of this talk, I'll be teaching you how to win data science competitions. Now they're about predictive analytics, and it's different in a consulting environment, so I'll touch on that. And unfortunately, last month, Terry Speed gave a talk on big data, and unfortunately I was elsewhere, so I couldn't attend, but I thought it was a good opportunity to kind of give my 2 cents about the big data hype that's going on at the moment, and how I feel statisticians fit into there. Whether you agree or not, I'm not sure, but we'll see. So here's I think a nice sort of schematic from Conway about data science versus statistics. And his basic idea here is that a statistician will probably have maths and statistical knowledge and substantive expertise, which is domain expertise. So you might regard statisticians being in the traditional research part. And in his schematic, what you need to be for data science is the addition of hacking skills. Now, the way I interpret that, it might be hacking programs, of course, computational programs, or it might be hacking data. So these kind of skills you gather from experiences in hacking is probably the difference between statistics and data science. I wouldn't say it's the difference between a data scientist and a statistician necessarily. I think a statistician is normally considered a bit more narrower than a data scientist, whereas here you've got data science essentially being within statistics. And there's also a nice thing here where, with the danger zone, that he sees that if you have domain expertise and hacking skills and you don't have maths and statistical knowledge, it's a dangerous position to be in, which is saying you should get some statistical knowledge, which is good. So it's a nice schematic which you may or may not have seen before. I like this one. This is quite nice. It's a Google Trends, but it's not statistics versus data science. This is a Google Trends plot of a statistician versus data scientist. And the word data science was used quite frequently back in, say, 2006, but the word data scientist was not necessarily. And I think this is a nice trend about, statistician versus data scientist. Statisticians have always been there in the public eye, but more recently, in the last, say, 4 or 5 years, the idea of a data scientist has become more favourable and has been searched more and more. And as of the beginning of 2014, data scientist has overtaken statistician. So the question is, why is that? I don't know. I think, well, this is how I view myself, and on LinkedIn, I'm a data scientist. And by the way, if you're a statistician in the audience, just try and change it from statistician to data scientist on LinkedIn and see what happens. I guarantee you'll get more interest from things like that. On my email signature, I'm a data scientist, and to market myself to internally within CSIRO and externally. And why do I do that? Well, I think if you're marketing yourself to clients or people outside of your area, I think data scientist kind of gives a sense of a more broad value across an organisation. It's particularly important in CSIRO that you promote yourself internally in particular to people who run projects so that they employ you. Unfortunately, as of today, it's probably the first time in modern history that CSIRO does not have a statistician in the sort of top 100 senior most people. And so, it's very important now that we sell ourselves internally to our organisation. But that doesn't mean I'm never a statistician. I think the statistician I see is more specific, and things like academic conferences, things like providing expertise to journal articles, or being an expert at a meeting, client meeting, a technical expert. That's when I kind of take that statistician role. But certainly for general promotion, I tend to use data science. So the question is there a greater demand for data scientists? Well, there's a startup company, which you may or may not have heard of, called Xpify. And their idea is to kind of link up freelance data scientists with companies who want to employ data scientists. So the idea is that they're the middleman and they deal with the contractual issues and the data user agreements and things like that. And it allows the freelance data scientists to earn money from those companies. Similarly, the Melbourne Data Science Meetup, which is this one, if you're in the SSAI, that's the other group we're joint with here. That's only been around for not so long, and that's got a lot of people, which suggests some demand. But Kaggle Connect had similar aims to Xpify. So Kaggle is the data prediction competition website. They essentially had this thing called Kaggle Connect, where they would link up people who were successful at data mining competitions with companies. Now that didn't work out for them. So I don't want to misquote them, but I think their basic idea was that they thought it was a niche in the marketplace, and there was a lot of interest from data scientists and companies. But when it came down to it, they didn't really have the demand to sustain it. So if we're talking about money here, when I got the email from Xpify, that was talking about somewhere between $50 and $200 an hour. In Kaggle Connect, when I was involved in Kaggle Connect, when you put in your bids, it must be at least $200 an hour. But Xpify is more general, and Kaggle Connect was specifically for people that have done well in prediction competitions. So that might compare to, say, a company like CSIRO, where probably in a larger project, you might be charging sort of 300 to 400, but then you're covering the costs of the contracts, and the overheads and stuff like that. So it'll be interesting to see how Xpify does, given that they dropped Kaggle Connect and it didn't work for them. But certainly there seems to be a demand out there. So if I go back, the difference between the statistics and the data science is the hacking skills. What kind of skills would you need? So I'm talking to the statisticians now. And kind of here's my breakdown, I would think. This is more in terms of programming, but I would say there are two essential skills. One is you need some kind of stats modelling, which most statisticians would have. I think also you need some kind of data manipulation, data munging, or scripting type languages. So I think they're really the two essential skills, either for doing data mining competitions or data mining in general. So probably it's the second of those that a statistician wouldn't have necessarily. I also think there are lots of additional data science skills. I wouldn't regard these as essential, but they were useful. Kind of lower level fast computation language, compiled language, C or Java or something like that. A knowledge of sort of data storage, SQL type databases and sort of newer non-SQL type stuff. Again, I don't think that's essential, which may surprise you. A lot of statisticians, particularly those that work individually, might not even use databases so much. Certainly if you work in groups, you certainly use databases. And another additional skill is kind of big data technologies, which I'll talk a bit about later. So I guess I'm partly known for data mining competitions, so I'll teach you how to win one. There's only 3 steps involved in the data mining competition. Okay. So the first thing is the data manipulation. Okay. And the second thing is the machine learning or statistical modelling. And the third thing is the ensembling. And I'll do an example in R in a bit, a very short, quick example. So the idea is you've got your data set, you can make transformations, take out variables, do what you want with it. You've got various machine learning tools you can apply to that data set to do your predictions. And then you do that lots and lots of times, for lots and lots of predictions, and then you throw them all together. And that's your ensemble. Okay. So let me give you some more general advice, and I'll give you an example of 2 and 3. So I'll do a quick example in R with a very simple, well-known data set, where I'm looking at different machine learning methods and I'm ensembling those predictions. Okay, so here's my general advice. The first bit of advice is just because you have the data, it doesn't mean you have to use it. So I got in the top 10 of an algorithmic trading challenge competition, and I used less than 1% of the data. Okay. And the reason is the form of the data, because the thing I wanted to predict for about 99% of records, the thing I wanted to predict was 0 in the data set. So clearly the information was only a tiny part of that data set. And for a camel competition, it was quite a big data set. It was a few gigabytes in size, which I think put off a lot of people. But it was quite clear that it was only a small amount of that data that was relevant for that prediction. So that's the main thing. Don't feel you need to use all the data. It might not be relevant. Another important thing, if you listen to Phil Briley's talk for the R group, I think it was, a few months ago, he said this. Probably said it better than me. There's no such thing as a single best model. Okay, there really isn't. Data mining competitions are virtually never won by a single model, a single method. Okay. They're won by lots and lots of predictions, all merged together. And that's because different methods can look at different features. Okay. One method might pick up certain features, another method might pick up other features. It's like a committee of individuals. You want diversity in that committee so that people have different opinions. Just like with having you don't want a single person. You want lots of different models, lots of different people, all reflecting different aspects of the thing you're trying to predict. And the other thing I would say is just to visualize the data. Lots of funny things happen with data. If you visualize it, you can see that. Okay, some more advice. If something takes more than a minute to run, I generally don't bother. Let me give you an example. Suppose you're trying to work out the predictive accuracy of some model. So you do a 10-fold cross-validation. Do you really need to do a 10-fold cross-validation? Can't you just do a 3-fold cross-validation? Does it really matter that you're trying to get it most accurate? Because bear in mind the data set you want to predict you can't see anyway. Or do you even need to do a 3-fold cross-validation? Why don't you just take 2/3 of the data set as a training and 1/3 as a test? And use 1-fold of the 3-fold cross-validation. So you're always looking to do things quicker, because often it's not really as important as you think. Okay. But try and look to do things quicker. Maybe you can sample the data and test things with smaller data sets initially. Okay, don't try and get bogged down with these long-running things. The other thing I would say is try and spend more time on trying different models with different data and different data transformations. Okay. Don't focus on choosing parameters, okay, to the 4th decimal place, okay, to get the best accuracy under a test set. Okay. It's better to spend your time on a variety of different models than really trying to estimate parameters to the nth degree. The other thing I would say is just have a go, try and submit predictions of 0 or predictions of averages or whatever, and then you'll be on the leaderboard, and then you can only go upwards from there. There is a downside though. Okay, so here's the downside. It can be quite addictive, okay, and it takes time. Okay, so how much time? Time is valuable. How much time do you have? You have to bear that in mind. If you don't have much time, then I would say don't have a go, right? Because it will probably suck you in. Okay, I'm going to put up some statistical methods which generally work well with most data sets, and some statistical methods which generally don't predict well with most data sets. This is a generalization. Different things happen with different data sets. But in general, these are the models I would go to first when I'm doing a data competition. And in brackets, I've got the packages in R, which allows you to do those models. But if you're using something else, then packages will usually be available. So these are my kind of first things I go to when I'm doing predictive analytics. So the first things and they're usually pretty good across a wide range of data sets. Gradient boosting machines, which are basically boosted decision trees. Random forests. Elastic nets, which is a word for basically regularized, generalized linear models. Do you know what they are? Where your regularization term goes between an L1 and an L2, depending on the parameter. So if you didn't understand any of that, don't worry. It just gives you predictions. Okay. Support vector machines can be quite useful. Neural networks can be quite useful. I've kind of ordered them in what generally works best. So, and this kind of isn't all the time, of course. It depends on the data set. But generally, gradient boosting machines tend to work best in most of the examples I've been in. So a really good thing about random forests is it's basically idiot-proof random forests, because you can basically put in any parameters and you'll get a half-decent prediction. I think with gradient boosting machines, you often do need to tune those parameters, shrinkage or the number of trees or whatever, to get a good result. I think neural networks is probably the most difficult one to use. You've really got to make sure that your numerical optimization works properly. There's always a danger when you're using neural nets that when you come to do the final model on your whole data, it doesn't optimize properly and it gives you complete nonsense. So in terms of usability, I would say random forest is the easiest and neural nets is the most difficult. So here's some that I probably don't bother these days even going to. A single decision tree is really not going to get you anywhere. Nearest neighbour has never worked very well for me, I must say. Nearest neighbour methods. Mars stuff, multivariate adaptive regression splines, generally not that competitive. Naive Bayes, not that competitive either. So those are the ones I generally wouldn't bother going to, certainly not in the first instance. Okay, so I'm going to give an example now in R, and what I'm going to do is I'm going to run through with a very famous data set and a very small data set. I'm going to run through a predictive model using the first three of those. Okay. The first one's going to be a gradient boosting machine, the second one's going to be a random forest, and the third one's going to be an elastic net. So let me run through this. Okay, so what I've done here, I'm just loading the packages. And I'm going to use a really famous data set, and statisticians, anybody who's done a stats degree would have probably analysed this data set about 10 times already, because it's one of those data sets that everyone uses. And it's the iris data set for iris flowers. A few smiles in the audience. So I'm not going to use the species of flower. What I'm just going to use, I'm just going to use here, just do this and show you the data. I'm just going to use the first 4 variables. I'm going to pretend I want to predict the sepal length from the other 3 variables. Okay, so very simple and straightforward. And then what I've done is I've split my data set into a trainer and a test. I've taken only about 10%, probably a bit small, but never mind. So I've got a training data set, which I'm going to train my models, and a test data set, which I'm going to predict my observations on. So the first thing I'm going to do is that thing there, which is a random forest. Okay. So the idea here is I'm going to fit my random forest, I'm going to predict my test data, and I'm going to come up with a metric to evaluate that prediction. And in this case, it's just a mean squared error metric. So it's pretty much the default values, actually. Entry is normally 100 default, and mtry by default is a third of the variables. This has only got 3 here. I've got 2. So it's pretty much just the default parameters. Okay, so they're my predictions. So my predictions for model 1, which is M1, is PM1, which is here. So they're my predictions, and that's the mean squared error of those predictions. So next thing I'm going to do is this, which is a gradient boosting machine. Oh, incidentally, a couple of quick tips for you in R. Avoid using formula objects because they take up loads of memory. Okay, so don't use formulas. Use the interface which allows you to put in the matrix directly. And the other thing is use matrices for your data. Don't use data frames because that can really slow down things if you use data frames instead of matrices. So this is a gradient boosting machine. Let's see how this does. Oh, it does a bit better. Obviously this is an error metric, so you want it smaller. So this is 0.154 and the other one was 0.153. So here's my third model that I had in that list. And that's a GLM net. I'm going halfway between an L1 and an L2 penalty with that alpha equals 0.5. So let's see how this does in my predictions. So it does slightly worse actually, 0.159. So what would I do here? Let's just get these predictions up. So those are the values. Now you could say, oh well, model 1, which was my random forest, that's the best model. But remember my general tip is there's no one best model. So there is no best model. Okay. The best model is usually found by combining your existing models. Now there are lots of clever ways to ensemble. I'm going to use a very unclever way. I'm going to ensemble my predictions by taking the average, okay, which is a perfectly valid way of ensembling predictions. So let's have a look at this then. Let's take the model for predictions, which is the average of 1 and 2, and let's take the average of 1 and 3, and let's take the average of 2 and 3. The first thing to notice is all of those are better than any one individual. And this often surprises a lot of people. Even by just taking the average of two sets of predictions. If you use the average to predict, you generally do better than using any individual one. Okay? Not necessarily, but generally. I can, of course, try all three. See what I get there. And in fact, I do about the same as I do about the same as I did by just averaging the first two. So sometimes it works for you, and sometimes it doesn't. You have to try it out. And don't discard something that's not very good, because something that's not very good might be looking at a different aspect of the data than all of the rest of your models, and so actually might ensemble quite well, even though individually it's not too good. Having said that, if it's really bad, it's probably not going to do very well. But don't just dismiss something if it's not too good as an individual model. So there's a very quick way of showing that ensembling actually does work, even if you just do it by taking averages. And in fact, in most data mining competitions, the experienced people, their first submission won't be a model, it will probably be a blend of 5 to 10 models. Some of the important concepts in predictive analytics are actually not focused on much in statistical teaching, which is things like overfitting, things like regularization. Okay. These are quite important concepts which I think are probably more, I think, not all statisticians, but I think a lot of statisticians may not have the awareness of the importance of avoiding overfitting when making predictions. So I'll put these slides up on the web, so all the code is there, you can test it yourself. So clearly, competitions is not really like working for clients. The problem with the predictive analytics is that any method that's any decent is a black box, basically. Okay. In fact, it's worse than that, it's actually lots and lots of black boxes, all rolled into one. So that's difficult, and in practice you have this issue of simplicity versus predictive accuracy. So you've really got to know what your client wants. Okay. We often use, say, a single decision tree. Okay, it's very poor at predicting, but sometimes that's not the important thing. Okay, sometimes it's the understanding of what's going on. On the other hand, some clients might not want to understand what's going on, they just want the outputs of the predictions. So it's always important, you get a kind of wide range of clients, from clients that are quite scientifically literate and really care about what you're doing. On the other hand, you might get a client that his boss told him he had to do this, he's not very interested, he has to spend the money before the end of the financial year or whatever, he's going to throw your report in the bin. So it's important you kind of know where on that line your client lies. So I guess reporting is an issue. It's always nice to give variable importance measures. Even these black box techniques, you can come up with variable importance measures. And that's always quite helpful, I think, even if you don't understand the black box of the implementation. Because the other aspect is the client going to implement this themselves eventually. Okay, so any questions before I go on to talk about big data? Yes?
Do you have some good ensemble methods?
Good ensemble, that's a good question. Well,
Can you repeat the question, please, Alec?
sorry, so the question was, do you have any good ensemble methods? So, what a lot of people do is something called stacking, where you actually employ a model to your predictions from each of your models. So it's almost like a second-tier model, and usually it's something like logistic regression or something like that. So you actually use your predictions as regressors to come up with a new set of predictions. Another thing is weighted averages. Sometimes it's quite important and sometimes it's not. It just depends on the data and how things go. But taking an average is usually a good first hit. I mean, it's not like it seems really, really simple, and therefore it should be really, really poor, but it's not necessarily so. Sometimes taking an average is actually not too bad. Any more questions?
Do you use collaborative filtering?
Collaborative filtering, I don't personally know. So my knowledge on that probably isn't as good as yours. So I'll probably leave that. Yes, Evan?
I guess the more general question is that data science? I mean, is data science equal to predictive analytics?
Yeah, that's a good
There's
question.
some sort of
So data science is not equal to predictive analytics, and that's a good point. And so data science has a lot more to it than just prediction. I've looked at the predictive aspect here. There are aspects of explanation, aspects of visualization. So that's a good point, and I probably should have pointed that out myself, is that here I'm focusing on the predictive analytics side. Of course, there's a lot more to data science than that.
Do you only work in predictive analytics?
No, I work in lots of areas. It's just I think sometimes a client might want predictions, but sometimes not. So it depends. So I go on to talk about big data, and maybe we can talk about this because Terry picked up on it last month, and I have no idea what he said because I wasn't at the room. But I'm going to give my opinion on it anyway. So I've gone to quite a few of these sort of big data conferences, and often you get talks where you get quotes from people who really love big data and say it's the next big thing, and then you get quotes from people who say it's all hype and all rubbish and that sort of thing. I didn't really want to go down that angle. I just really explaining my take on things. So big data means different things to different people. I remember I was at a conference once where the first speaker was talking about the Square Kilometre Array, which is a radio telescope in Australia and South Africa. He was saying, in a few years' time we'll be bringing 10 petabytes per hour. And the next speaker at this big data conference was talking about a data set with 1,000 rows and 9 variables. And I thought, big data really does mean different things to different people. I think, and correct me if I'm wrong, statisticians, but most statisticians would consider a few gigabytes to be a huge data set. Now, if it's a flat file with a few variables, you're probably talking in the tens of millions of rows. And so there's clearly a gap there. And so I think it's important to realise that when people talk about big data, they're often talking about different things. So they might be talking about the 10 petabytes per hour, they might be talking about the thousands of rows data set. So I guess the question I'll look at is do statisticians have a role to play in all this? And I'm sure data scientists have all seen this before. I'll just go through it. The statisticians may not, but big data, we often talk about the 3 V's of volume, velocity, and variety. I guess sometimes people talk about 4 V's, and the 4th V seems to either be veracity or value, depending on who you talk to. So that's the basic idea of big data. I'm going to skip the hype cycle, because I've probably heard it before. So this for me is a typical sort of statistician. Okay. So I'm on dangerous ground here, this being a statistician. So I'm going to be nice. So most of the statisticians I speak to, bear in mind I am one, okay, will say that they're really involved in big data. They're heavily involved. It's really interesting, and it's used a lot for marketing purposes as well. But again, it comes down to that it's different things for different people. Okay, they might say big data, they might be talking about data that you can still fit into memory. I think when you talk about technologies, that's where it kind of breaks down. Okay? When you talk about map-reduced jobs, when you talk about Pig or Hive or Hoot or these sorts of things, have you ever programmed a map-reduced job? Then you get to the stage where the answer tends to be no. Okay. Or I haven't actually heard of what that, or I don't know what that is. Or I've never done that. And I guess the question you ask is, why is this? Okay. Because I think you learn these things when you need to. And so the basic thing is that statisticians haven't needed to. And certainly, I think most statisticians will never use a data set over, say, 0.5 terabyte or something like that. Yeah, you're talking about several gigabytes as a maximum. So, in fact, well, while I'm here and I have statisticians here, let me ask. Well, let me ask first. Let me ask this. Who here has programmed a MapReduce job in any language? Pig, Hive, Java? That's good. Put your hand down. So put your hand up if you're a statistician from the Stat Society. Okay. Now put your hand up if you're a statistician and you've written a MapReduce job. Oh, you're in. That's good. There's two people, so maybe I'm wrong. But I think if you speak to most statisticians, they really won't have any idea what any of these things are. So, I guess we've got 5 to 10 minutes left, so let me just say what I think statisticians have a role and where I think they may not have a role. Okay. So I think statisticians have a role in things like developing what data is relevant to the question at hand. And that may involve, sampling big data, subsetting big data, modelling subsets of the data, those types of things. I think this is where I depart from the, well, I'm trying to be diplomatic here, but when I depart from a lot of other statisticians is that in some aspects, statisticians I do not think have a role. I know I might get some strongly worded emails from the Stat Society members, but that's okay, I can handle it. I think if you have a large data set, like 0.5 terabyte or larger, and you want to touch all the data, and that's important. Okay? If you want to touch all the data in a 0.5 terabyte data set, I don't think statisticians have a huge role. Now that's a big if, and maybe a statistician might say, well, do you need to touch all the data? But if you want to touch all the data, the problem is you're restricted to linear algorithms, or possibly linear arithmetic algorithms. So you're looking at sums, averages, maybe linear arithmetic, graph searching, sorting, that kind of stuff. And it's difficult to see where statisticians have the role there. And I guess my evidence for this is the lack of statisticians that know about these big data technologies, which will allow you to chunk through these and do sums and averages. And this restriction, of course, parallelization doesn't do anything for you. I mean, you can't get out of the mathematical fact that parallelization will just affect the constant of the running time. And even if you had infinite memory, you can't get around the fact that as you get up to these huge amounts of data, you're restricted to linearity in the running time. And so I think statisticians have less of a role there. So, in fairness, I think they have a role in some aspects, and then in some aspects, they don't have such a big role. So I'm going to finish by just showing you an email I got sent yesterday. And there's a lot of text here because I can't misquote things. This is an email from ANU advertising a workshop. And I think this is where statistics is at in big data. So there's lots of words here because I don't want to misquote. What was interesting to me about this workshop on robust statistics and extremes, I do a lot in extremes, was that the first paragraph is all about big data. Okay? It's about big data, extremely large data sets in astronomy, finance, physics. It's an exciting time to be a statistician. And then the second paragraph actually talks about the workshop. It's nothing to do with big data whatsoever. Okay? And I thought when I got this email, well, that's where I feel statistics is at. They're talking about big data. But for genuinely large data sets, they don't really have a role to play, and they're not playing a role, and they don't really know about those technologies which will give you that role. And maybe they're not talking about big data, they're talking about your sort of gigabyte-sized data. So, I guess the conclusion is that if you're a statistician, one of the few statisticians that knows about all these big data technologies, and you're interested in the terabyte-sized data sets, then maybe you shouldn't call yourself a statistician. So I will finish there. Thank you very much.
Many thanks. We'll take some questions.
Hi. I'm wondering, is there an iris equivalent for big data? I mean, we've been teaching statistics for many years, and that's how we learn the tools and the methods. And there's been people putting an effort into creating the tools to help us learn it. So is there anything in the big data space that you can point to equivalent of iris that's got all the characteristics of a bigger data set that we can go to and play with and learn and teach?
Yeah, I mean, sorry.
Sorry, Alec, would you mind summarising?
Yeah. So summarising data was, it's about whether we can teach this and whether we can provide data sets. I think the question is, it's pretty easy to provide data sets. You can just scrape the web or whatever. I guess, I think the teaching of big data in statistics classes is very difficult. In some sense, it might be distracting from the actual statistics elements. Because what you can do with big data is limited in genuinely big data sets, like terabyte-sized data sets. You'll be, well, you would never use terabyte for teaching, even if it's few gigabytes. You'll be getting them to do things which are quite difficult, and I don't think would help them statistically, because it would be impossible to fit, say, a quadratic algorithm for a statistical model for a data set of 100 gigabytes. So. The question is, if you're doing a statistics class, should you be teaching the skills of big data? I think that's the question. I don't know.
Damian.
How often do you need to touch all the data?
Well, that's a good question. I mean,
Sorry, Alec, would you mind repeating?
sorry.
It'll help with the video too, if you repeat all
So
the questions.
the question was, how often do you need to touch big data? That's a good question. I mean, you could argue never. Okay, that would be a very un-big data answer. I think you probably need to touch it less than. I think that in most circumstances you don't need to touch all the data. And maybe the point you're making is that that's when the statisticians come in. I think that's a valid point, that maybe a statistician could say, well, do you really need to chunk all this data? Is it worthwhile? So, in a lot of cases, you're right, you don't need to touch all the data.
What do you think about Mahout, actually? The algorithms on top of the big data technologies. So it helps statisticians, or will it help other people?
Yeah, certainly. So the question was about something called Mahout. And so for those that don't know, Mahout is basically trying to get try to extend machine learning algorithms to larger data sets. And it used to do that through MapReduce. I think it may have changed lately, but essentially parallelizing all these machine learning routines. That's really useful for going through relatively big data sets in quicker amounts of time. But again, parallelization, it makes things quicker, but again, it only makes the constant lower in the running time. So you're still not going to be able to do a quadratic algorithm in terabyte-sized data sets, even with Mahout.
Isn't one dimension of big data non-numeric data, like text and free text, and that is one area where statisticians might find themselves struggling to make a contribution?
Absolutely. So we talked about the 3 V's, and I concentrated on volume. So what you're talking about is variety there.
Yeah.
And it is a struggle. I think statisticians are used to doing data with genetics and with videos and photographs. And if you've got sort of unstructured text, particularly if you're a statistician, you don't have a scripting language, and you've got these gigantic text files of unstructured text, that's where the problem comes in. And so certainly you do need those that's where I kind of think the scripting type skills are important when you have these types of unstructured data.
You mentioned Mahout and the fact that they're changing the underlying technologies. So Google, although it embedded MapReduce, isn't using it anymore internally, so they're moving forward. How do you see the field changing with the online algorithms, and particularly multi-unbounded type solutions? Do you see it simplistic solutions coming out of some of these technologies, or becoming more sophisticated?
Yeah. So the question was about is the fact that Mahout has moved away from the MapReduce framework. I must admit I don't know exactly the details. You appear to know more than me. I think we will see. I mean, I didn't show the hype cycle, but there's always a lot of hype around these new technologies. I think once things settle down, they have a benefit, but the benefit is probably not as much as originally hoped. So it'll be interesting to see what happens to Mahout now they've recently dropped the sort of MapReduce paradigm.
If you're dealing with like millions of records and thousands of variables, do you really go down that visualization path, or are you pretty much just tapping around the forest and let it do itself?
No, I mean, I do.
Yeah.
But in terms of visualization, so the question was, if you've got millions of rows and lots of variables, do you visualize things? And I honestly do, but I don't necessarily visualize the entire data set. So it's really just about getting a feel for the data. So you might sample the data and visualize. But I always make sure I'm looking at something, because at least it will sort of throw up gross problems and things like that. So even with hugely data sets, if you just extract from rows with a scripting language and load them up in R and visualize, I think it still helps.
I was just wondering a little bit what your definition of a statistician is, or what the definition of statistics is. Just going back to that Venn diagram right in the beginning, by the end you seem to be sort of saying that there's an area of big data that statisticians don't belong in or something. Somehow, I guess because of the current training and so on that most statisticians have, but I'm sort of curious as to what the sort of conceptual underlying sort of issues are. Like those of us who've grown up with a fairly broad view of statistics, sort of think of it as understanding data variation. We haven't grown up with the technologies to deal with these huge data sets, but that's a sort of a technological gap, admittedly. But I'm not sure that's sort of helpful to say that sort of inherently statisticians don't belong in some space and they belong in another space. Does that fit in that Venn diagram, or are you departing from that?
Well, if I can summarise the question, I guess it's really about, you're really asking about the definition of statistics. And that's a good point. Shouldn't we just broaden the definition, right, to adapt to all this new technology?
It's been around a long time, the idea of statistics. The Royal Statistical Society, they're counting at the sheaves of wheat, sort of thing.
I mean, I guess I view a statistician more in the sense of a statistical modeller, which is probably where I'm coming from. And that, if you have a gigantic data set, say, the entire network of Facebook or all the pages on the World Wide Web, you can do really interesting stuff. But ultimately, because of the size, let me go back. Because of the size, you're really just taking sort of sums and averages and counts and things like that. That's the only thing you can do, really. And that can be very interesting. I'm not saying it's not very interesting. It's very interesting because of the data. Okay, but the actual statistics aspect, that's not very interesting. You're just counting things. You may be counting lots and lots of things. You're still just counting things. So I guess my question is, in that context, when you can only run things that are linear, the expertise of the statistician can't really be used in its full form unless you're going to sample or subsample, or sample or subset or whatever.
You're just saying that statisticians don't have expertise in some areas of data science without really explaining to me what they are. There's some sort of black boxy things that you can do non-linearly that are somehow, useful with these huge.
I think the question was about, what expertise are statisticians missing, and I think the main thing is the big data technologies, and they're newer. But I think I would have expected more statisticians to pick up on them. They were really interested in these large data sets. And 2 people in the room said they were statisticians and they knew about these technologies. So maybe what I'm arguing for is the statisticians who are interested in this to learn these technologies.
purple shirt.
When you're running machine learning on a big data, huge data set, how do you tackle that? Do you first sample small subset and then run it on your computer, try a few models like iris data set, and then do the same thing for the big one? Or you go run, let's say, random forest or something like that on the cluster?
Yeah, I mean, as long as you can kind of fit the data set, well, that's what I generally do, so that's exactly what I do. So as long as the data set isn't too big, you can fit it into memory, maybe it's like a gigabyte or less. You can do that, so you can do it initially on smaller values to get an idea of the accuracy of your method. And then you can use the entire data set, run those machine learning algorithms and those predictions, and if you're doing a competition, you could submit those predictions. So the actual last run might take a long time, might take 2, 3 hours, 4 hours. But I would never run something which was 2, 3, 4 hours while I was developing.
Two questions, or perhaps that's two things, part of the same thing. As scientists, we're basically concerned with trying to understand causes. As data analysts, statisticians, called what you like, we have models, and you use the word model. Where does model come from, and where does it come into the thinking?
So that's a really good question, and this is, when you do a search for big data on the internet, there's people who think it's the best thing since sliced bread, and there's where I am, which is that it's a bit overhyped. And this is the argument which I completely agree with, is that, where's your question, where's your model? And these are all things that, the big data tends to brush over in a lot of cases. So I agree these are all very important issues. And of course, these sorts of issues are where the statistician comes to the fore, I think, in developing models to answer important questions.
I'm neither a statistician nor a data scientist, but my question is, what sort of expertise should be run over this sort of stuff to make sure it makes sense? I mean, as a client, you purchase black boxes, but you'd like to know somebody who you trust tells you that what's coming out of the black box makes some sort of sense. So is it a statistician? Is there some other expertise? I suppose it goes similar back to the modelling question. What should you be looking for?
So the question is, if you're from the client perspective, how do I know that things coming out of this black box make sense? And I think, it's really the statistician that looks at that through doing things like, creating test and validation sets. I think you really know that it makes sense when you wait for the future and you see how good it is. So, I mean, that's, if you're going to make a prediction, that's the gold standard of how good your predictions are. You wait until the event happens, and then you see how close you are, right? Like the weather forecast. So there's loads of publications on evaluating weather forecasts and things like that. So who do you trust? Well, you trust the statisticians.
Ian. I guess my question is a follow-on from Daryl's, and you addressed it a little bit, but I can see how the thing that you showed us for the iris data set could be extended to, or applied in situations where the predictions would be of real interest. But no scientist with the iris data set would be satisfied at all with that kind of approach where you're just predicting, I forget what the outcome was, the sepal length or something on the basis of a bunch of new leaves. Because they'll measure all the things on the next ones anyway. What they want to understand is what is really going on in terms of the association between them, or being able to understand the botany behind what is really going on. They're not just interested in a sort of black box that will tell them what the sepal length may be on the basis of the 3 other measurements, which is really just Daryl's question applied to the iris data set, I guess.
Yeah. So I mean, the question was, on the iris data set, you wouldn't clearly, it's a small data set, you wouldn't practice like machine learning algorithms, but on the point of the question is that you would want to understand the process, and that's where your domain expertise. What's happening with the process, and then you can model the process and get better answers. I'm totally in agreement with that, and this is why I'm on the side of the people that think the big data is quite a lot of hype, because it doesn't address those issues of understanding the process, whether it's a physical process, whether it's in psychology or in botany, understand the process and then use your statistical modelling to model that process. And certainly, you often get better results with small data doing that than you would running a black box machine learning algorithm through a big data.
You're comparing statistics and data science, but you're flipping when you talk about data science between, say, machine learning and big data. And they're not the same thing. A lot of machine learning is useful with gigabytes of data. So I'm kind of interested, I think that the overlap and the interest is between statistics and data science, and that you can build all of these different models, but there actually there's clearly value in having a statistical understanding of what's going on, or what might be going on, or how you might improve it, or even how someone's going to come up with the next model that isn't being used, or a variation on the model. And that's where there's a clear overlap between the two approaches.
Yeah. I agree with those comments.
So there's been a bit of revolution in big data and the availability and collection of large data sets. But as you pointed out with your example, there's been a bit of a revolution in little data methods as well. The machine learning examples you gave there, the statistical modelling that's improving a lot, and we can do a lot more now than we could even 15 years ago with the methods that are available. Have you seen much stomach in public and private sector organisations to make more use of improved little data technology?
Well, that's difficult to say. Clearly, the methodological aspect is improving all the time for these things. And I think people are getting better at doing these things, particularly in predictive analytics. Is there a stomach? Well, I think it depends on the commercial viability. Does it really improve your bottom line? Really, is what it's about. So, sometimes in the commercial sector it can be really important to get a little bit more accuracy, and in those cases, those people are really interested, and sometimes it's not so relevant. So, it's a difficult question to answer. So sorry, I should have repeated the question. So the question was about the improvements in little data, or gigabyte or less size data, and whether that's of interest to the commercial private sector.
To what extent is the big data hype generated by software companies pandering to middle and senior management who feel that they should get into this, but have no clear idea of what they're getting into and why? Because that's where a lot of this hype comes from. I'm not neglecting the really good uses of big data I've found have been the scientific big data sets which have been gathered for a purpose, an experiment possibly, and analysed accordingly. But often I find that there's lots of big data sets, lots of big data techniques being touted by people who've got no real interest in the science or even the relationships, but more in the profit they can make.
Okay, so the question was about that lots of big data set techniques are touted by people who know nothing about it and interested in profit, and I would say that's absolutely true. You'd get a phone call saying, well, let's do this big data stuff, and somebody who their incentive is commercial, because they know it's the hype at the moment and they feel it would make them some money. And so I think a lot of it is due to.
One last question maybe before I close up.
Where do you see the industry going in the next 1 to 2 years?
I don't know.
That's a prediction.
let me predict. Well, I think the hype cycle schematic's fairly accurate on this. So I think once I think the hype will die down, but hopefully we can make lots of money in the meantime.
Well, great answer. Thanks again to ThoughtWorks. We've made an appointment at the Hop House on South Bank, so please join all of us and the speaker for dinner and drinks. Maya, did you?
I just, in case you haven't found the toilets, they're out the main doors here, to the left, women's, and all the way to the far more men's. And yet, I guess the other normal bit for OHS is if anything catches fire, please run around screaming with your arms waving.
Okay, and you can, if there's any food left, grab it on the way out. So it remains just to thank those who've helped out tonight, and especially to Alec Stephenson, our speaker. Thank you.